While we learned in 12.1 about permutations, which means orders of items where the order actually matters, in 12.2 we begin discussing combinations. And a combination just means a group of things that you have in your hand. So I have an entire cup of pens and I'm going to take 3 things. And now I have these 3 items in my hand, and it doesn't matter what way I hold them. I could rearrange them in a couple of different orders. And I still, if I was looking at what I had in my hand, I would say I have a mechanical pencil, a regular pencil, and a pen. And so the order here does not matter. So when we are looking at a combination, the order does not matter, right? It's the same group that we have. So let's think logically, what does that mean? When the order doesn't matter, it means I could have a whole bunch of different groupings that I am counting that are all repeats of each other, because I could have them lined up like this. I could have them lined up like that. Could have them lined up like this. And yet it wouldn't matter. I would still just have one set of these 3 writing utensils. So when we come to combinations, it's going to look a whole lot like our permutations, with the exception that we're taking out duplicates. We discussed that with 12.1 at the end of taking out parts of a group that were duplicates. But in this case, where I have my entire group in my hand, everything that I move around in this group is a duplicate. So instead of a portion of it having a duplicate, for example, having 2 of the same pencil, yet I still have 2 different ones that matter whenever the order matters, and we're looking at it. Instead, I'm saying this entire group, it doesn't matter how I hold it. So the entire group is now a duplicate. So what that does is that takes our permutation formula of n number of things, taken r number of things at a time, and we can expand that to a combination. Combination means order doesn't matter, of n number of things taken r number at a time. So let's look at how we worked here. Permutation said if I had a total number of items taken in a group of n minus r factorial, so total number of items taken a certain number at a time, this helps me get rid of all the ones that I didn't want to take. A combination says that I have a total number of items taken a certain amount at a time, and I'm going to factor out any duplicates. So in this, we maybe put in different spots for the duplicates every once in a while when we had some, and we would take them out. In our combinations, it's saying the entire group of our things that I have taken is a duplicate, because it doesn't matter how I hold it. So what we've really done is we've just expanded our permutations into a combination where the entire group is a duplicate. Combinations are read exactly the same as a permutation. They are still read a certain number of things taken, certain number at a time. So if I have cards, a 52 deck of cards, I would say a combination of 52 cards, and I'm going to deal out 5 to everybody, taken 5 at a time. This would be written, I know I have a hand of 5 cards. So going back to our fundamental counting method, what would our numbers be here? It would be 52. Then once that card's taken, I have 51 options, then 50, then 49, then 48 options. And I want to get rid, with my factorial, I want to get rid of everything below from 47 and below. So I have 52 factorial divided by 52 minus 5 happens to be 47 factorial. That gets rid of all the extra ones because I just wanted these five sections. But within this 5 set of cards, I could rearrange these cards in a lot of different ways and still have the same 5 cards in my hand. So if I took 5 cards and I put them in my hand and I just started, maybe I want to line them up by blacks and then reds. Maybe I want to line them up higher to lower. Maybe I want to go lower to higher. Maybe I want to put face cards together and number cards together. I can rearrange these cards in a lot of different ways, yet I still have just the same single hand of cards. And so I have 5 factorial because I have 1, 2, 3, 4, 5 spaces. That's also my R value over here. 5 factorial of combinations, different ways that I could rearrange that would all be duplicates within. So I have my original, here, and then I'm going to factor out my duplicates. As we study combinations, we can study combinations of combinations or combinations of permutations. And that means we're just taking more than one choice and we're combining with another set of choices. And something that's a good example about that is in using our cards, we have different suits in a card. So we have diamonds, hearts, the clovers, and a spade, right? And so we could say, I want to pick just one suit, and then I want to pick 5 cards from that suit. So how do we do a combination of a combination? When we use the word and, this was the same in our series that we were learning as well. When we use the word and, we are going to use multiplication. When we use the word or, we are going to use addition. So if I wanted to choose one suit and then from that suit, I wanted to pick 5 cards from that suit, I am looking at lots of different choices. So for my first choice, I am picking one suit. And for my second choice, I am picking 5 cards from that suit. So in the first choice, I have 4 options. For the second choice, within each suit, there's 13 cards. So I had 13, 12, 11, 10, and 9 to be able to have in my hand. We would write that using combination notation saying for the first one, I had 4 objects or 4 different events taken one at a time. And then for the second one, I would have 13 cards taken 5 at a time. Because we have and, we would be multiplying that together. So that is telling us that I have my first choice, and then I can multiply times the different sets that I have for my second choice. And we can use our combination formula and just plug in and get those. So now we have the option of having combinations of combinations, and you could have a lot of different ones that you would multiply. If we are choosing or, if it is an event where we would be choosing or in the middle, we would be adding the different combinations together. In our lecture today, I talked about going to the theater, and it said you want to attend at least 3 plays. So we could say we wanted to go to 0 plays or 1 play or 2 plays. Because we were using or, we added up the combination amounts that we got in the middle. So if we're using or, we're adding. If we use and, we would be multiplying those together. On your homework, for a couple of those, when it's written, a combination of 10 things taken 2 at a time, we're going to simply plug it in and say I've got 10 things, so 10 factorial, taken 2 at a time. If I'm using the fundamental counting method, I would be putting 2 blanks saying I've got 10 options for my first one, 9 for my second one. And then I've got duplicates here, so I have 2 ways. Every time I do it, I would have to be dividing by 2. So I'm going to divide this. So 10 times 9 divided by 2. which is my duplicates. Let's see if we get that. We've got 10 factorial. 10 minus 2 gives us 8 factorial. So that cancels out. 10 times 9 times 8 factorial is another way of writing 10 factorial. So I've canceled out all the ones that I didn't want. And I'm going to do my r factorial, 2 factorial for my duplicates. So with my formula, I ended up with 10 times 9 over 2. We got the same thing both ways. So this is the logic way using our fundamental counting method here on the left. Our combination formula is used on the right. All right. If we have for 26 through 31, it tells us, say for 27, we have 4 aces and 1 other card. What would we want? How would we find this? So there's a couple of different ways. We're choosing 5 cards, so we could use our fundamental counting method. We could say, I've got 4 aces, meaning these 4 spaces all have to be aces. And then this space can be anything else that we want. We started with 52 cards. If I take out the 4 aces, I'm left with 48 other options. Now, if I want to pick all 4 aces, that means I have to put an ace in each space. Because the order doesn't matter, I'm not doing 4 times 3 times 2 times 1. That would be if the order mattered. Remember, so technically, if the order matters, I would have 4 factorial divided by my duplicates, which would be 4 factorial, still gives us 1. So right off the bat, I can go ahead and just plug a 1 in there, saying I have to fill all of these spaces, so I've got 1 option for each of them, and then I have 48 other cards that I can choose from. So 1 times 1 times 1 times 1 equals 48. If we were writing this in combination, we would say 4 aces taken 4 at a time, and 48 cards, 48 other options taken 1 at a time. That would give us the exact same numbers that are multiplied out.